Our experimental setup comprises a visible white wall from which there is a hidden monitor an unknown distance away. There is a rectangular occludent object of unknown position between. An ordinary 4 megapixel digital camera is pointed towards the wall. The camera's field of view is shown in green. An unknown pattern is displayed upon the monitor. The light from the monitor hits every point on a Lambertian imaging wall, apart from those which are occluded. A measurement is then taken with the camera by combining multiple exposures to give an effective exposure length of around 3.5 seconds. This method is used as the input to our algorithm, which aims to reconstruct the images or patterns displayed in the hidden scene. For a given scene, feeding the captured image through our computational algorithm recovers an estimate of the hidden object and hidden scene image. In addition to being able to clearly resolve the larger features like the general shape, redness of the head and yellow face, smaller features such as the white patches are well resolved, and hints of the even smaller features such as 2 eyes and the unibrow are also visible. The transport of light from the monitor to the imaging wall is linear. By using a suitable discretization of the monitor and imaging wall, we can form a light transport matrix which describes the forward model. The presence of an occluding object in the scene is extremely important, as it provides a significant boost in the conditioning of the light transport matrix by introducing greater variation between the columns due to the discontinuities it creates. This usefulness of occlusion is particularly clear when considering a simple scene of only 2 monitor blocks illuminated. Without the occluder, it is not possible to intuit the pattern which is displayed from the measurements. With an occluder present in a known position, it becomes obvious to a casual observer that there are 2 blocks illuminated on the same row. For a more interesting scene, the camera capture becomes a mixture of the diffuse light radiating from the hidden scene, punctuated by shadows and penumbra cast by the occluding object. This phenomena improves the conditioning of the inverse problem of reconstructing the unknown hidden scene from a single camera snapshot. Without an occluder, this problem is extremely poorly conditioned. The presence of an occluder establishes a computational field of view in the hidden scene. The computational field of view is the area in the hidden scene from which the camera field of view includes penumbra from at least one edge of the occluder, and thus benefits from improved conditioning. The best conditioned region, depicted in blue, is the region in which the camera field of view sees penumbra resulting from all of the occluder edges, thus providing even better conditioning. Different occluder positions emit different computational fields of view, with shifts in the X and Z position resulting in respective shifts in the computational field of view. Similarly, changes in the distance from the imaging wall to the occluder, or the occluder size, result in scaling of the computational field of view. When the postulated occluder position is incorrect, we observe a deterministic, predictable shift in the reconstructed image due to the shift in the computational field of view. The shift is a function of the distance between the monitor and wall, the monitor and the occluder, and the offset of the postulated position from the true position. Here we see different shifts in the transverse or X position of our postulated occluder and the effect this has on the reconstruction. We leverage this phenomenon in the final reconstruction algorithm. Similarly, a change in the Y position of the postulated occluder results in a predictable scaling of the reconstruction. The full reconstruction algorithm comprises multiple stages. Firstly, the camera measurement is acquired and split into 3 color channels. We can then form one estimate of the hidden occluder position for each of these 3 color channels and take the average of the 3 estimates to form our final estimated occluder position. We do this by leveraging the fact that the camera measurements lie in a low-dimensional subspace which is dependent upon the occluder position. We can project the camera measurements along the range space of a simulated forward model for a given postulated occluder position. Maximizing the norm of this projection with respect to the positional parameters provides us with a maximum likelihood estimate for the occluder location. We use the estimated occluder position to simulate the forward transport matrix. We then take differences along the columns of the measurement image to reject slowly varying and close to constant background contributions, before solving a total variation regularized inverse problem to form the final reconstruction in C. Presented here are a number of reconstructions achieved in the scene described. Column A shows the ground truth image displayed on the monitor, and column B shows the camera measurement that was acquired. Column C shows the result of the reconstruction algorithm following the occluder position estimation. Column D shows the reconstruction achievable with a different algorithm which combines various shifted reconstructions formed using transport matrices where the assumed occluder position is varied. Lastly, column E shows the reconstruction achieved if the occluder position is known a priori and not estimated. It's clear that our technique is able to estimate the hidden occluder's position with sufficient accuracy and also form reconstructions which resolve even small details in the scene of interest, such as the eyes of the mushroom and the blue cross on the hat of Tommy. In addition to the single snapshot reconstructions, we also demonstrate a video reconstruction. Each of the 7 frames were reconstructed individually using measurements acquired with a sub 1 second exposure time and with the occluder position estimated using the first frame only. We can therefore demonstrate the reconstruction of a 1 frame per second video in the hidden scene. Lastly, we demonstrate reconstructions of both 2D and 3D, fully reflective, floodlit scenes made of colored cardboard. The occluder here used is non-black and also 3D. In summary, we have demonstrated 2D color reconstructions of a hidden scene from a single, non-direct snapshot captured by an ordinary digital camera, without requiring motion or a source of controlled illumination in the direct line of sight of the hidden scene.